When we put magnesium metal into aqueous hydrochloric acid, the two react. Aqueous magnesium chloride is formed along with gaseous hydrogen.
Now that we know a little bit more about what happens to systems in water, we can start to explore the concept of what's called a net ionic equation. And a net ionic equation, also known as a net ionic reaction, same thing, is it's basically a way for chemists to tell what the action of the reaction is. You're going to see that when you do a net ionic analysis, some of the chemicals just kind of sit there and they don't really do anything, all right? This is kind of like if you've ever been in a group project for a class and like you and your other partner is working really hard and the third person just kind of sits there and stuff. And oh, the joy of working in groups. But anyway, in chemistry, it's kind of the same thing. Down there, we have magnesium metal, MgS, magnesium with all its electrons. It's reacting with hydrochloric acid and it makes hydrogen gas and magnesium chloride. So in this particular reaction, we've got magnesium, H, and Cl, and one of those three atoms is not really doing anything. So the question is, how do you tell? And the answer to it is we're going to go back and think about what it means to have something that's aqueous. Because remember, if you have something that's aqueous, that means it dissolves. And if it's a strong electrolyte, which most of the ionic compounds are, they break apart 100% into their ions. So we don't really have HCl at all. In this reaction, we really have H plus and Cl minus. That's what the aqueous can tell the chemist. If you look over on the product side, aha, another aqueous, aha, another ionic compound, because magnesium is a metal and chlorine is a nonmetal. This is also going to break up into the positives and negatives. So you're going to have a positive 2 magnesium floating around, and there you're also going to have a Cl minus chloride running around. Now, what I just did, analyzing for positives and negatives, you don't want to do that for things which are solid liquids, which aren't shown, or gases. So if you had any compound that had a S, L, or G, solid, liquid, or gas, don't break it up into the positives and the negatives. But everything that's AQ, and there's a lot of them in these examples, you do want to break up into positives and negatives. So let's rewrite this equation with the ions showing, because really it's not 2HCl AQ as we talked about. This would be 2H plus aqueous plus 2Cl minus aqueous. And MgCl2 is not MgCl2 in this example. It would be Mg2 plus aqueous plus 2Cl minus aqueous. And if you look at that equation long enough, kind of looks like 2Cl minus on the reactant side and 2Cl minus on the product side. Chemists don't want to write things twice if we don't have to. So those Cl minus there, which are present on both sides when you break apart the aqueous pieces, those guys are just kind of sitting there. The chemicals that just sit there and don't do anything are like the third person in your research group that just sits there while you and your partner do everything else. And in chemistry, we call these spectator ions. They are not participating in the chemistry of the reaction. And there's actually a really cool thing that pops out of this. In this reaction, it was magnesium and hydrochloric acid making hydrogen and magnesium chloride. Well, since the chlorides were just sitting there, we didn't have to use hydrochloric acid and you'd still end up with the same result. We could have used nitric acid, HNO3, and nitrate would have been the spectator. That would have been just sitting out and boring. So spectator ions will appear on both sides of the reaction when you break the aqueous pieces down, and they are not part of the chemistry. They're not part of the action of the reaction. So the net ionic equation essentially cancels the spectator ions out. Like in math, if you had 2x on the left and 2x on the right, you would cancel them out. We're going to do the same thing in chemistry. So the action of the reaction, the net ionic equation, magnesium metal plus 2H plus aqueous makes H2 gas plus magnesium 2 plus. That's really what's happening. Magnesium, as we're going to see in this chapter, is giving some electrons to H+. It becomes magnesium 2+ in the process, and you end up with hydrogen, the diatomic gas. There's a handout in the companion and online which goes into more details about net ionic reactions, and I do encourage you to check it out. So the top part is the molecular equation. That's what we actually added in. This part right here is the net ionic reaction or net ionic equation. And to go from the top to the bottom, we had to pull out the spectator ions. Chloride was the spectator ion here.
A solution of lead nitrate is added to a solution of potassium chromate. A yellow precipitate of lead chromate forms, leaving potassium nitrate in solution. The potassium and nitrate ions do not take an active part in the reaction.
This is the reaction between potassium chromate and lead 2 nitrate, and a cool yellow solid there kind of appears. You can see in the video. That compound we're going to see is lead 2 chromate, PbCrO4 plus potassium nitrate. Now remember, anything with potassium and anything with nitrate is AQ automatically. So K2CrO4 is aqueous, PbNO3 is aqueous. And on the product side, the KNO3 is also aqueous as well. But most of the time, the big negative polyatomic ions like chromate and permanganate and stuff like that, as long as they're not with sodium, potassium, ammonium, stuff like that, most of the time they will be insoluble. So we will put an S next to it. Chromate is very insoluble, again, as long as it's not with an alkali metal or ammonium. So when you go through this reaction and you pull out the spectator ions, you're left with the net ionic reaction, which is essentially the formation of the lead 2 chromate from the lead 2 plus ions and the chromate ions. So this reaction had 2 spectator ions, both K plus and nitrate were spectators. Notice in the molecular equation on the top that the K and the NO3 on both reactant and product side are both in aqueous forms. And that's another way to look for the spectator ions in these when you're doing them. This question says what are the spectator ions in the following reaction? 2KOH plus FeCl2 aqueous makes FeOH2 solid plus 2KCl. So like we said earlier, if the ion is in aqueous pieces on both the reactant and the product side, then it's going to be a spectator. And notice right away that on the product side, KCl aqueous is there. So we're going to be looking specifically, at least what I would do, for K plus and Cl minus. And so sure enough, K plus is here. It's with the AQ part, so we know K plus is a spectator. And Cl minus is also in iron 2 chloride, which is also AQ. So this particular reaction has 2 spectator ions. Both K plus and Cl minus are spectators. This net ionic reaction, you would pull out the K plus and you'd pull out the Cl minuses, and you'd be left with 2 OH minus aqueous plus Fe2 plus aqueous, making FeOH2 solid. All right, pretty sloppy, but hopefully you get the idea. That would be the net ionic reaction. It would not include the K plus or the Cl minus, which are spectators. Some of the previous examples have been examples of what's called an exchange or double displacement reactions. And exchange reactions or double displacement reactions are very common in chemistry. If you have 2 species coming together that are ionic, so A and B here would be the positive cations, and X and Y would be the negative anions. You can think about this as like a dance, and everybody changes partners. So instead of A dancing with X, A ends up dancing with Y, and B, instead of dancing with Y, ends up dancing with X. So an exchange is literally like a type of a dance where you trade partners. This is a chemical version of that process down there, PbNO3 plus 2Ki, making PbI2 plus 2KNO3. What happens is the lead and the nitrate trade places. Lead ends up dancing with iodide, potassium ends up dancing with nitrate. Now notice that all of the charges are the same. So lead is a +2 with lead-2 nitrate. It's a +2 with lead-2 iodide. And potassium is +1 both times. That's why you have to have the 2's right there. So in these kind, the cations are trading places with the cations, or the anions are trading places with the anions, and they're pretty common in chemistry.
When we combine solutions of lead nitrate and potassium iodide, a colorful material appears. This is actually a solid called lead-2 iodide.
PbI2 has kind of a neat yellow color, like you can see right there. It's pretty spectacular. That's the insoluble compound. That's why we write that as an S, all right? It actually is showing up as a solid. The KNO3, the spectator ions, are just kind of hanging out on the side and watching the leads and the iodides come together to make the PbI2. One type of double displacement or exchange reaction, which is really important, is called a precipitation reaction. And these are really important to chemists overall. We're going to start talking about the things that drive chemical reactions to happen, all right? And one driving force, one reason why reactions occur is if you can form an insoluble compound. And in my world, an insoluble compound is called a precipitate. So in this reaction, we've got iron 3 nitrate and sodium hydroxide reacting. This is a double displacement. The the iron and the sodium are trading places. Iron starts dancing with hydroxide. Iron 3 hydroxide is insoluble. Most hydroxides that aren't with sodium, potassium, ammonium are insoluble. Sodium and nitrate always AQ. So when you pull out the spectators, both the sodiums and the nitrates, you end up with Fe3 plus 3OH minus, making FeOH3, an insoluble precipitate. This is called a precipitation reaction. This is one of the 5 types of reactions we're going to look at in Chem 221.
In the test tube, we have an aqueous solution containing iron 3 ions. To this, we will add a solution of sodium hydroxide. A precipitation reaction occurs that produces iron hydroxide, an insoluble metal compound.
Iron 3 compounds oftentimes have that kind of off yellow color that was initially in the solution. But when you add the hydroxide to the iron 3, you end up with that brown precipitate. That brown precipitate is the iron 3 hydroxide. That's the insoluble precipitate that formed in this reaction.